And if you've got this already and you're like, yeah, I'm fine with this, maybe you just want to watch out and make sure you haven't gone too far in a circle. Induction is circular in a sense, because this is why we talked about this being dangerous before, right? We are sort of starting where we ought to end, right? So you may feel like you're going in a loop, but you shouldn't do multiple loops. Just do the one and end up where you started, okay? If your solution is fine, you can go on with these ones, okay? So if it's a bit confusing, I want to prove that n cubed minus n is always divisible by 80. Okay? And some of them are very counterintuitive. Like, you look at that one, divisible by 21. You're like, really? How do those things turn into 21 times 21, 42, 63? It's weird looking, okay? So anyway, let's keep going. Where are we at? I've now got my setup for my proof, so I'm going to take the left-hand side, and I'm going to go from there. Okay, what's that equal to? You can see already, you just kind of have to muck around a little bit with your indices, right, and know your index law as well. So I've got 3 to the 4k plus 4, or minus 1. Okay, so because up here in the index I have a sum, that's going to convert to a product, right? And I might as well mention, because they're really the same thing but in reverse, right? See how I went from a sum to a product, right? Indices, exponents, exponentials, and logarithms, right? You know, they're inverses of each other. So that's why when you've got an index, a sum can be expanded into a product. When you've got a log, it's exactly the other way around, right? When you've got a product, you can expand that into a sum, okay? So that's how they work, they're in reverse. Right? And let's keep going, minus 1 on the end here, okay? Now, at this point, I look and I think, I've sort of expanded out, there's not really much else to go here, except for our assumption, right, which is here, okay? So how can I massage my assumption so that it can fit into this, okay? You may have taken the 3 to the 4 and seen, the 3 to the 4k, and notice you've got that here, right? You just got this 3 to the 4 that's in the way, right? So you've got 2 alternatives here, okay? You could change this so that it has the 3 to the 4k minus 1, okay? And then you can substitute that for your ADP, okay? Alternatively, and I've seen a few people do this, which is why I'll draw attention to it now, maybe you want to take the 3 to the 4k and just substitute that. If you wanted, that's fine. However, I can't do it at the moment because I don't have 3 to the 4k equal to something, right? My assumption's a little different. So I'm going to work a little on my assumption first, provided I've done this earlier, right? I can say 3 to the 4k, just looking at it from the other way around, is ADP plus 1. I've just shifted the number over, okay? And what that does, if I make that my statement that I assume, I can bring that in quite easily, right? So what do I have here? I've got ADP plus 1 times 3 to the 4 minus 1. And this, I've got to make sure I say why I've made this substitution. Okay, so by assumption. Please, please, please include it. You might be so caught up in actually getting to the answer you forget to say this. Okay, so make a special note. Okay, where do I go from here? Well, apart from the p, these are actually numbers I can deal with, right? So that 3 to the 4 is 81, right? So I've got ATP plus 1 times 81 minus 1. And I can expand here, right? Now, I could say, what's 81 times 80? Okay? I'm not going to. I'm just going to leave them as separate terms. You'll see why in a second. Because I'm going to have to refactorize. Remember where I'm trying to end up. Okay? I want 80 times something. Okay? So if I've got 80 times something, I might as well leave it in that state. Okay? So I've got 80 p times 81 plus 81 minus 1. So I can simplify this. 80p times 81 plus 80. Okay, I'm almost there. Can you see? It's a bit trickier because what you're trying to prove has no p's in it, okay? But it's got a q, which is meant to be some other number. Well, what's the some other number? I can find it by taking out my factor of 80. Okay? What I'll have in the brackets is 81p plus 1 lot 80. Okay. Alright, now, what you might like to do on the side here, you don't need to include this, I don't think, in your working, but just so that you understand what's going on here, okay? I would say as p is an integer, right? Since p is an integer, therefore 81 times p plus 1, right? That thing is also an integer, right? You take a whole number, you multiply by some other whole number, and you add another whole number. Everything's talking in whole numbers, okay? So you should still be in the same step, okay? Therefore, I can make my next step, which is, well, that's equal to, since it behaves the rules that I set for q, I can just say, well, that's q, okay? That's the q I was looking for. That's q where q is equal to 81p plus 1. Okay, does that make sense? Almost got there, right? And that's done. There's my proof, so all that's left now is my explanation, okay? Therefore, by the principle of mathematical induction, the statement's true for n equals 1, n equals 2, n equals 3. So pretty neat, right? So this is why we're starting to get into this topic and how you can use it to prove. I mean, where would you go, really? Apart from, here's a few numbers and it works, okay? This is logical and it shows it's always true.